So electrophilic addition, in this case, notice that we have an asymmetric alkene, okay, because one, so be familiar with the skeletal formula, that's very important. We have one carbon here with a carbon group and then a hydrogen, and then we have the other one with the two hydrogens, okay? So the mechanism, same as before, the region of electron density is the double bond, so the nucleophile attacks the electrophile, heterolytic fission, and this will result in a carbocation. The thing is that the positive charge, where that is, it matters because it's in two different positions, and the addition of the bromine in the second step would give a two different products. Okay, the thing is to understand why one is major and one is product, but also remember that the rule, we could remember it like this. In an addition reaction of a hydrogen halide to an asymmetric alkene, the halogen bonds to the most substituted carbon atom. This could be the rule, like, okay, so the most substituted, so the one that has like other chains of, like, rather than hydrogen. So that could be a simple way to remember it. But it's really important to understand why that occurs. And this is because the major product is the product with the most stable intermediate. The most stable intermediate, yeah, is the one that we will see is it's most substituted. So this stabilization, it's called inductive effect. So this carbocation is stabilized by this, what is called inductive effect. Inductive effect is the donation of electron density through a bond. And important to picture electron density, okay? So groups that are different than hydrogens, they are bigger groups, so they have a lot of electrons. And those electrons can move towards that positive carbon to make it a little bit less positive. So the more neutral the intermediate is, the more stable, because if it's charged, it's not really stable, but it's stabilized by this donation of electron density. So a primary carbocation, it has this donation just by one R group. R, it's an alkyl, so different than hydrogen. Okay, so that's important. The R group is just something that is different than hydrogen. A secondary, notice that it has two groups that can kind of neutralize, or stabilize anyway, that carbocation, while the tertiary one has a stabilization from all the groups. So this is the most stable. And we can think about the mechanism that we have and think, okay, where can the positive charge in the intermediate be? Can be on either side of the double bond. So which one would be the most stable? And you can identify by looking if it's a primary, secondary, or tertiary. So in this case, we have a primary carbocation, because notice that this carbon only has one alkyl group, while this carbon has two alkyl groups. So this would be our secondary carbocation. This is our primary carbocation. So we know this is the most stable intermediate. And where the positive charge goes, so does the bromine. So one tricky thing is to identify what it's a primary, what it's a secondary, how is it possible? So let's do some examples that I would say it will help understanding this concept of a primary and a secondary. So let's take this. Okay. Okay, maybe could be a bit complicated to look at as a skeletal formula, so we can also draw this plate, but with the focus on the double bond. So let's think what's around this double bond. On the left-hand one, we have a CH3, and then on the top hydrogen, because there's nothing. The other one has a CH3 and this other group, C2H5. Okay. So we can see already that this carbon has two carbon chains attached. Okay, and this is what it will make it a secondary. While the other carbon has one carbon chain, another carbon chain, and another carbon chain. So this will make it tertiary. If we can't visualize it because this is just the alkene, we can always think, okay, let's assume it's reacting with an hydrogen halide. hydrogen delta positive, hydrogen delta negative. So the attack will always be the same, nucleophile, so our region of electron density to electrophile, but then we could have the first step, which is the addition of hydrogen on both of them. So let's think about what's the consequence of that. Okay, do you want to try to write it down? So those are the two options we can have. The positive charge on either of the carbons, and we can think about which one would be more stable. And we can just identify by looking at the groups. So we know that this one has 3 different carbons attached, so it's going to be a tertiary carbocation, great. While this one has just a 2 carbons, so it's going to be a secondary. But why is that? So when you really to picture, to try to don't think anymore about these dots and crosses, but think about electron density. So all of these groups have electrons, and those electrons, they will stretch onto this carbon carbocation, and by donating this electron density, they stabilize it, okay, because they don't make it as charged as it actually is. Yeah, it's more stable. And if it's more stable, it's more likely to form. Okay, so like this, by doing this analysis, so the electron density is just something that I would like to try to picture of this movement of how really this inductive effect works. But to identify which one will be the major or the minor product is just by looking at, okay, which one is the most stable carbocation, okay, and the most substituted, so in this case, the tertiary would be. So the goal here is not only to understand why secondary, tertiary, it's more stable, but it's to identify then the major and the minor product. So because this halogen will add on this carbon, it would be our major product, and therefore this would be our minor. So this is the way to understand it. Otherwise, Markovnikov rule is a bit easier to remember by saying just that the halogen bonds to the most substituted carbon, so the one that has the most carbon. Or you can remember it the other way. Well, the hydrogen adds to the least substituted carbon. I think, though, let's avoid memory and just fully understand this inductive effect, because like this we can always work it out. And then I would say you will get to a confidence level where you can just scribble down the mechanism and work out the intermediate that is formed and do a bit of analysis. Okay. And one thing to mention about this is that this electrophilic addition, it doesn't matter which electrophile we have, the mechanism is always the same. But here are some examples of other addition reactions. So we have hydration, where water is added. Again, in this case, we have 2 products simply because we have an asymmetric alkene. Just halogens, which is actually a good test for the alkenes as well. As we saw, the hydrogen halides. So all of those are addition reactions. Just this is not an addition reaction, because as you notice, we go from a double bond to a saturated hydrocarbon, but the change really is that hydrogens have been added. In fact, this is called hydrogenation catalytic because we use nickel as a catalyst, or also called reduction. Okay, so it's important to analyze these. We no need to know the mechanisms, but it's still a type of addition in a way, because this is the typical reaction that alkene do. Okay, so to summarize, addition reactions, the mechanism is it's always the same: nucleophile to electrophile, carbocation intermediate, and then the last step. And then, well, the electrophilic addition of asymmetric alkenes will give 2 different products, one which will be major, the other one which will be minor, depending on how stable the intermediate is. Good. So I hope that clarifies the topic.